Hi, hello everyone. I'm Oliver Gao. I'm the director of Cornell System Engineering Program. I have been very fortunate to conduct what I call these system conversations with our prestigious speakers that we invite to Cornell. Today, I'm very honored to introduce to you Professor Chris Cassandras. Actually, Chris, he is a distinguished professor of engineering at Boston University, and he is actually the head of the division of system engineering. I would love to learn more about that division because at Cornell we have this system engineering program also cutting across, but sometimes we come across some challenges. So and also he's a professor of electrical and computer engineering and is a co-founder of Boston University's Center for Information and Systems Engineering. So I just want to briefly mention Chris' research. He specializes in the areas of discrete event and hybrid systems, cooperative control, stochastic optimization, and computer simulation with applications to many different areas, from computer and sensor networks to manufacturing systems and also transportation systems. And I think this is really good. He's not only looking to this fundamental system science and modeling, and he's really bringing his research to the real world applications. So Chris, welcome to Cornell. Welcome to this conversation.
Thank you very much. Yeah. It's really a pleasure to be here. In fact, I should point out that to my knowledge, there aren't a lot of places in the US that have systems engineering PhD level programs. Yours is a program. Ours is, we call it the division, but we started out as a program too, where we didn't have an academic home, really. It was interdisciplinary, picking and choosing from different departments. And then about 10 years ago, we decided to create a division, which is an academic entity with its own staff, budget, programs, courses, and so on.
Wonderful. So I'll probably change my order of questions since you started talking about this, because this question is so dear to me. You're right. You mentioned the word a home, and especially in a given all this traditional disciplinary structure that the colleges have been set up, and we have this new thing, especially this new thing cutting across all the different disciplines, and also as this system engineering as a discipline is yet to be mature, to be established. When you think about what is the core, fundamental thing of system engineering, it's hard for people to answer, very clearly. So speaking of that, here at Cornell, the system engineering program. So for example, we can draw faculty from different departments. However, the commitment of the faculty, right? If you think about when you have funding or you have research opportunities, people come. However, when you think about the services, all this kind of teaching, that really requires faculty commitment. Especially, we maintain this large, massive engineering program, which is actually a very important source of our funding support.
Same here.
For these things. So how on your side? So your faculty in the division, they do have their home department in those different departments, but how do you gain their commitment and loyalty?
Yes, so that's a tough question, but it's an accurate depiction of the situation. Once you create this interdisciplinary communities, call it programs, you have to get a commitment. So by having a division, the commitment is that if you're a member of the division and you're also a member of your home department, you're involved in the administration of the division. So we have, for example, a graduate program committee, which determines the admissions and also the curriculum structure, and the teaching of the courses. So we have our own curriculum, we have our own courses in systems engineering. However, I would say at the end of the day, there's a certain element of trust and collegiality involved.
Yes.
Because otherwise, as you very correctly pointed out, you can get into competitive situations. Everybody has a finite amount of time. So if you have a faculty member X and you tell them you're in, let's say, electrical and computer engineering and you have to do A, B, C, but you also have to do D and E in the division, at some point, the person says, I have to prioritize. So far, it has worked very well. More so than I expected when we started this experiment about 12 years ago now, I think. But there is, I would say it's a delicate balance.
It is.
It may take one person to say, I can't handle that. One thing that has worked very well for us is that we have our own admissions process, and we attract students, both at the PhD and the master's level, but let's say the PhD level, who come to study systems engineering, and they find a home in the division because there are courses, there is a staff that takes care of them. We, for example, help them very much with internships and job placement, which they appreciate. And they are very high quality.
Yes.
And so if you're a faculty member, let's say again of electrical and computer engineering, and you see these high quality students that fit your research area and are well prepared, of course you would want to work with them.
Yes.
And then you have a stake at the division's well-being.
I agree with you. I very much agree with you, and it is kind of especially our PhD program was launched back in 2017.
So you're fairly young.
Yeah, we're fairly young.
Yeah.
But I think, Chris, one thing that I'm very pleasantly surprised. You see, we started in 2017. Now it's 2023, and this fall we have 54 PhD students in the program, and it's exactly due to the mechanism because we have good students. For example, some faculty in their own department in their traditional area, they cannot find the very good match student applying. However, system engineers, they see this thing. So because our policy is that system engineers provide about 1 year of funding support for all these new things, and after that the faculty members will pick up.
We have the same system.
Yeah, the funding
we
support.
give them a fellowship.
Yes.
To come in, and then they have to find a research home.
Yeah.
So very, very similar
Yeah.
philosophies and so on, and very similar numbers.
Yeah.
You said 54.
Yeah.
I would say our PhD population right now is in the order of 45. So very close.
Yeah, I think this is very nice. So speaking of this, right? I think when I talk about commitment, and I think one key thing I agree with you, it's really the genuine alignment of the faculty's interest and the program. It's like in a kind of, if you have some faculty, their research interest is genuinely related to this system engineering area, that kind of connection will just naturally happen. You
Yes.
don't even need to do much.
Yes.
All right. However, if it's not very well aligned, and then you cannot force it.
Yeah. So here's where something that's happening organically, we are not forcing it because we like systems engineering, is helping us. And this whole movement towards the term that's used these days is convergence of research.
Oh.
Convergence is a term that a lot of the funding agencies are using these days. If you Google it under National Science Foundation, you'll see convergence. Convergence, they promote that. And we are adopting, it's really another word, I think, for interdisciplinarity.
Yes.
So, along the lines of what you were saying, if a faculty member in a certain department is involved in a research project which is interdisciplinary by its nature, you really need expertise from different areas. And a student comes into systems engineering with that philosophy and that desire to be interdisciplinary, they are the perfect match. So I would, if I'm running such a research project, I would prefer the student with the interdisciplinary philosophy and the preparation, because of the courses that we offer along these lines, than a student that might be very good, excellent, but very narrowly focused. He or she might help a part of my project, but if the project is so interdisciplinary, I'd rather take the systems engineer.
That's great. You're talking about system engineering research in the division. So one thing is that I think you and I probably are in the simple. I have a home department in civil and environmental engineering. Like my grant proposal submitted through civil engineering. So, but in your division, system engineering division, so do you have how? I don't know how the research is managed, or how that in addition to this intellectual this convergence value that faculty see as this division, does the division provide any other support or any other added value
Yes.
to attract faculty to
Exactly.
to the research.
And that's yet another way to answer your earlier question of how do you get the commitment
That's
of
right.
faculty. So we face the same problem as you.
Yeah.
Where do I go for my grants and my proposals and the grant management? We started out by doing it in our home departments for a few years. So roughly, if we started around 2011 or so, let's say until about 2014, 2015. But very soon we realized, first of all, because we were doing very well, we were generating a lot of grants in different departments where the same people were collaborating.
Mm-hmm.
So we already had created, before the division, a center for information systems engineering, which you mentioned earlier.
Uh-huh.
That had originally been created independently, but it became very natural to think of the Center for Information and Systems Engineering as really the research arm
Mm-hmm.
of the division. And at some point, with some help from the dean at the dean level,
Yes.
we created a grant management, a finance team at the center. So the center now manages all of our grants, unless if you're a member of, let's say, mechanical engineering or civil
Mhm.
and environmental engineering, you want to stay in your own department. That's fine. That's your prerogative. But if you have such a more visionary, interdisciplinary program, we have the mechanism. We do it through the center, which manages the grants, the proposals, pre and post award, and that has worked extremely well.
Oh, that's the key. That's the key. Because I think for faculty, right? It's kind of especially given this kind of convergence research funding sources coming in individual faculty, and even an individual department cannot do that.
Yeah.
So and then this kind of center doing that.
Yeah.
I think that's the
And we have distributed that way the
Yes.
work. It makes more sense, and in addition, there is a return of overhead, which you could get through your own
Yeah.
department, but the center is a bit more generous.
Yes.
So
Yes.
it provides a little bit more flexibility that way.
How does as a department view the center?
Yes, so very positively, very positively.
Because they get the funding.
They,
Through their
they
faculty.
also get, anyway, they get ultimately the faculty funded.
Yes.
Some of the students in the departments as opposed to the divisions benefit. And what we have found is it offloaded a lot of the work that had to be done on the management of proposals and grants. So if suddenly, 20 proposals and grants from mechanical engineering are transferred to the center, that's offloading a lot of work. And that is very, very important to the departments.
Who and how did you get the funding to support? I assume this pre and post proposal, and this is like a grant proposal machine, right? You have this machine,
Yeah.
and
You can think of it that way.
right. I think that's the key. And for this machine, where did you get money to build this machine and support this machine?
So that was organically created, as I'm sure you know. There are two ways to build these sort of entities in the university: top down or bottom up.
Yes.
Top down works sometimes, but it's not natural sometimes. You have to have a dean or a provost or some department chairs who say, let's do this. These people sometimes 3 years later they leave, they go elsewhere, there's no continuity. But if you do it bottom up, like we did,
Mhm.
back in 2003 or 4, about 5 or 6 of us from different disciplines decided this was a good idea. We pitched the idea first to the dean
Mhm.
of the College of Engineering and then further up the hierarchy. People said, hey, if you're bringing good grant support and you can self-finance the first part of the center
Mhm.
as a first phase, we'll provide a couple of administrative staff members, which is what they did, and then let's build from that. And that's how it started. We convinced the administration to fund, essentially give us some space and a couple of staff members, but really at a very low level. Then everybody got excited, things got going, we started bringing good funding support levels. We became self-sustained, but lean. We
Mhm.
were not overly ambitious.
Mhm.
The dean started seeing that, I said, that's good, let's grow.
Yeah.
And we then grew, and at this point I would say we have the blessing and the support of the dean, and further up we report to the dean as opposed to other
Yes.
centers that report to the vice president for research.
Uh-huh.
So we are within the College of Engineering, as opposed to being to the university.
Which I think is the right thing.
Which I think, at least at this
Yeah.
point, is the right thing. I agree. That may change, but so far we're happy with that. So we are not growing, exponentially.
Mhm.
We're growing within control
Organically.
and organically.
Yeah.
And so people are happy with that. They feel a sense of, academically speaking, a sense of accomplishment and pride that they did that without the top-down approach. And so they have bought into this concept. And now the staff of the center itself, which is the entity that supports the grant mechanism and so on, has grown a little bit, nothing special, but there are 2 or 3 other people. There's a person to handle, marketing, and there's a person who handles communications, beyond marketing. By communication, usually we mean things like websites and things like that, relationships with the local industry.
Mhm.
We really try to take advantage of our location in Boston,
That is an advantage, which we don't have here yet.
which you don't have here, yes. It's a big advantage because there's a lot of industry which cares for our product,
Yes.
and also allows us to establish internships. Very important. Our students appreciate that a lot, usually by the 2nd or 3rd year of a PhD's career. We have now a network of these companies that fit very well with systems engineering.
Yeah.
Different application areas: robotics, biomedical, software, energy. We every year we channel maybe 10 or so summer internships. Sometimes now, in fact, we do it even during the year. I don't necessarily support that idea. I'd rather have the students during the academic year focus on their academic.
But the student might like it.
It depends on a case by case. If it's a perfect match where the project in industry matches the person's PhD, why not?
That's
Right.
right.
And they're across the river at worst.
That's right.
Or across the square. It's
Yeah.
not a big deal. So that's how the center has evolved and managed to reach a steady state.
I think this is wonderful. So Chris, for sure that I will definitely follow up with you
Sure.
in the future, because I think there are many things.
There are many things that are in common,
Yeah.
and in fact, as I was saying earlier, I don't know that there are many places in the U.S. that have this vision of systems engineering, whether you call it a program or a department or a division. It is more challenging because it's hard to define systems engineering.
That's right.
We're facing this. I've learned how to deal with that depending on my audience. But we have certainly good demand. At the PhD level, we get a good level of applicants from which we can be selective. From the local industry, clearly they're interested in this concept of systems engineering. And at the master's level, surprisingly perhaps, we get a lot of applicants. We keep the level pretty small, pretty low, but we get a pretty good demand.
That's great. So I think it's so with this. So Chris, of course, you see that you now, of course, you're directing this division and also this center.
I'm not directing the center, by the way. We have a separate person
Okay, I
who is
see.
the director of the center.
I see.
And they're called director, and I'm called the head of the division, and the departments have chairs.
Oh, I
These
see.
are all words. They don't
I see.
mean anything more,
So,
but just to
being
set the
head-
nomenclature.
Yeah, no, thank you for the clarification. Being the head of the division, and of course, can you tell us more about yourself? Because ever since after you finish your study, because I think it for many people it takes a path for people to find in the end. This system engineering, right? So, tell us more about your from your study all the way to your work and now, and in the end, I would like you also to tell us more about your vision for system engineering. Where do you think that is heading, and what should be the strategy for us to use to help move the field forward? But first, your path to system engineering, like yourself.
No, yeah, thank you. And you're right in saying that it's not obvious how one starts identifying as a systems engineer. There's a path that usually comes from a more specialized point, and then you realize, hey, I need interdisciplinarity here. And it's nice to see that the new generation of students are seeing that sooner than we did in our generation. So in my case, my background was always control systems. We call it systems and control theory, but traditionally it's control theory. Using classical control techniques and optimization, I was always fascinated by the idea of optimizing a system. And I got into optimal control, which is dynamic optimization. And game theory. I was actually fascinated by game theory, which is why I went to do my PhD at Harvard with Larry Ho, who at the time was Mr. Game Theory. He had written the classic papers and a book that's still one of the top cited books called Applied Optimal Control by Bryson and Ho. This is the Bible of optimal control, and it had a few chapters on game theory. And I caught him at a point in his career where he was changing interests. He thought game theory had been saturated at the time. Of course, now we know it's making a comeback. And so he convinced me to go in different directions and start exploring a new class of systems called, we call them discrete event systems. Systems which are not governed by the typical time-driven dynamics, differential and difference equations. They do not necessarily need to be updated at every clock tick. Instead, they could be updated whenever an interesting event occurs, and in between the events, the state of the system for that particular system did not change. Perfect example, the internet. It is a pure discrete event system. In the state of the internet, which is typically described by the state of the queues at different locations in the nodes, or the state of the routers, is it up or is it down, busy, idle, under repair, whatever. This is a discrete event system. In between any event, nothing is happening. So once you realize that, you start seeing that you need help from computer science, which had looked at these kinds of systems and called them automata. So we relied on automata theory from computer science. This was my first glimpse at the need for interdisciplinarity. I could not just rely on what I had learned in class but from classical control and classical models. I needed help from other disciplines. Computer science, operations research, because in operations research, you model a lot of resource systems, production systems, transportation systems. Again, you model them through discrete event systems. There are discrete entities. There may be packets, there may be parts in a manufacturing system, there may be vehicles or trains or planes. And then you bring them together, but there are dynamics. That was the interesting element that we brought from the control theory side. So, move 10, 20 years forward, I started looking at all these different systems. At first it was manufacturing production systems. Later on, I started looking at robotic systems, then sensor networks, and in the last 10, 15 years of my career, transportation systems. In all of these disciplines, I found that I needed more than just what I had learned in school as a student. I needed more, and I needed help. And I worked on grants with colleagues who covered other areas from other departments. For example, when I got into robotics, I had to understand how a robot really works, what the dynamics of a robot are. Mechanical engineering was necessary. That's to answer the question of how I got into sort of this concept of convergence and interdisciplinarity. Now, in terms of my current research interest for the last, I would say, 10, 15 years or so, I've gotten into transportation systems because actually it was a coincidence, I would say. I was fascinated by the parking problem in a place like Boston. I don't think you have such a serious problem here, but in Boston it's an amazing phenomenon. It's a cultural phenomenon. People fight over parking spots, and there are pictures of people that put cheap lawn chairs in a parking spot in front of their house to basically tell you, don't park here, this is my spot. So I was wondering, this is a resource management problem. Why can't we solve it? And I started working on it, and I developed actually something that we call the smart parking system for BU, which we implemented in parking locations within BU. I'm not going to bore you with the technical details, but I think it was the first time that parking was really smart in that it doesn't just tell you where the parking spots are. That's smart, but it's only half smart. The other part is you have to reserve the parking spot that you know is available. And in addition, since parking spots come and go, as you travel towards the the spot that was assigned to you, you may find a better spot in terms of location, price. So it has to be reallocated. So it's a dynamic reallocation resource management system.
Making the information flow.
Making the information flow and translating it to concrete actions, like route me now there.
Yes.
And so that worked very well for a while, and suddenly I started thinking, well, you know, if, for example, we have autonomous vehicles that populate all of these Uber, Lyft type of ride-sharing fleets, then if these vehicles move all the time and I don't have to use my car because I can move around the city with this, then that will open up more spaces that I don't need. These cars are not parking.
Yeah, the cars
and
are
I
all
can keep my
moving.
car in my house, so you'll open up parking spaces and garages that are useful urban surface or real estate in a place like Boston, which is very tight, could be transformed from a garage to a hospital, to a school, to something nice. That was the vision. Of course, getting to the reality is not so simple, but then I started becoming more and more interested in the state of the art in transportation. At the same time, people started talking about smart cars and smart vehicles, and that's how I got into this area. And it's definitely interdisciplinary because I know how to model cars and develop control strategies for them, but I don't understand what transportation engineers, or I didn't understand what transportation engineers had done for decades in terms of policies, common sense ideas, and identifying the fundamental research problems. And so it is another perfect example of an interdisciplinary area.
Yeah, I think, Chris, that's a perfect timing. And also, it makes perfect sense to me. You started with parking, because parking is a real resource, and you see this as a competition, and then that you by making it smart, as you said, you make the information flow, and then you route the actions to take full advantage. Because actually, the resource is it is enough. However, there is a confusion between owning it versus using it. Right. As a result, the resource is not fully used, and then you start and you do that smart thing. And then, as you are thinking about that, you say, okay, what if if cars do not have to be parked, if they're always moving, and this ride sharing, right, it kind of come in. And when the ride sharing come in, and then I think one key thing, if you want to make the ride sharing to be even more cost effective, what if you don't need drivers? Because drivers are the most expensive part, but cars are become less expensive. It's really, the drivers are the only variable cost.
Yes.
Right, in that. So then you talk about autonomous vehicles.
Yep.
Right.
And by the way, there's this striking statistic that 94% of all car accidents are caused by human error.
94.
94%. That's a well-known statistic. You can Google it, you can verify it. So what does that tell us? It tells us that if we automate at least part of this whole transportation process, driving and parking to some extent, we can perhaps not eliminate 94%, but even if we cut that in half, that is a tremendous advantage for us in terms of safety.
Yes.
Because once you have a computer instead of a human driver, computers don't drink, they don't sleep, they don't blink, they react much faster than you or me when they see an obstacle on the road. So the only challenge that remains is get them to do the right thing as quickly and as exploiting the amount of information they can process that you and I cannot, in a proper, safe, provably safe, reliable, and economically viable manner. And now the result might be the Internet of Cars that we all envision. And it is very interdisciplinary. You need a systems engineering approach to that, because it is a very large system, The interesting thing to me is that ultimately you still need to account for humans in this system. So you need them as members of the system, elements in the system. So you need to understand how they behave, how to interact with them, and it makes it even more interesting. So from a systems engineering standpoint, the latest thing that I have discovered in my own career in the last 3-4 years is that now I need to work with social scientists, something that I would have not dreamed of when I was the perennial engineer trying to solve engineering problems in my student and post-student career. Now I need social scientists to help me understand how humans behave, to help me understand how policy is made, to help me understand the economics. So economists, psychologists, urban planners, public health people, to tell me about the effects, for example, of driving cars through areas in which, for example, there's too much pollution that then causes public health hazards.
Yeah.
This is a perfect example of a systems engineer.
Yeah, that's actually my research. My research is looking at vehicle emissions and air pollution, dispersion, and then exposure risk. And I was even trying to imagine that if we are able to, in real time, distribute the air pollution information to the drivers and how they would choose a different route,
Yes.
using information to
Absolutely.
change the behavior.
Yes.
Right. So
Very good problem.
Yeah. So Chris, when you talk about this, and I agree with you, I fully understand why you are reaching out to collaborate with social scientists because it's essentially human factors are the only things that you cannot fully control, and two, that is a major source of uncertainty, and also as you mentioned for the safety issue, there is a major source of the safety threats or the safety problems, right? So I fully understand. So for that, and I think in your talk, Chris, you mentioned. So before I never thought very carefully, but from your talk today, you actually explained the difference between optimization and control. Right in your slide, on one hand it's optimization, on the other hand it's control, and you explain that optimization, right? You are trying to find optimum that will take resources. However, control does not need or cannot necessarily reach the optimality, but it works things out. So it's somehow giving me a sense of, in the real world management, we have to be in the trade-off between optimization and control. So what's your opinion? Because your talk kind of got me start thinking about, because control is real implementation, and optimization it's kind of helping you provide more insight to make a decision and then implement. You can see there are these steps. However, especially now this kind of real-time control, while you want to do some optimization, but you cannot. Right. So how do we balance these two?
I would say first of all, the offline optimization program provides you sort of the ideal solution. And then using a control, you try to get as close as possible as you can within your realistic constraints, but at least you know what you're striving for. Secondly, I would say ideally you want to do both. You want to do optimization and control at the same time, hence the term optimal control. In one case, mathematically speaking, you optimize statically over a set of parameters. So it's a one-time solution, and once you set your parameters right, you have an optimal solution. An example would be, let's say, a facility location, or what we call the coverage control problem. Let's say you have a forest susceptible to fires. You have so many resources, typically sensors to detect fire starting, sparks or heat sources. How do I optimally distribute them? Okay, that's an optimization problem. However, now suppose that you don't have that many of the sensors, but the sensors are moving. You have, let's say, only 10 instead of 10,000, and they have to keep on moving to serve the same function, but now it's a time varying problem of finding trajectories, not points, but entire trajectories
Yes.
of how these resources should be moving. Now you're in the realm of control and hopefully optimal control. So both ways of thinking and algorithms and practical methods, I think, are needed. The question is how to bring them together in a nice, balanced way.
That's beautiful. So it's essential, having the sensor, having the smaller number of sensors moving to cover the spatial coverage that you wanted to have, say, 10,000 sensors.
But I can't afford them.
You cannot afford you cannot afford them.
Yeah.
So with that, so I'm just curious, Chris. Did you compare? So assuming that you are able to afford, or for example, if the cost is about the same level of cost, but kind of good enough, not abundant,
Yes.
but a good enough number,
Yes.
a good enough size of resources.
Yes.
And then should we use less number sensor and a moving trajectory, or should we use a larger number but fixed? So which one is?
No, you're absolutely right. That's a trade-off. And yes, we're looking at problems like this. I'm actively looking at precisely these trade-offs, or to formulate a more precise optimization type problem would be, I can only afford so many of these resources. This is the bound. What is the best way that I should then be placing them? Or should I start spending more of my resources to make them move, which is more expensive, more prone to failures and so on. And as you say, you make comparisons and you formulate optimization problems and sometimes just feasibility problems. You set a standard. You say, if I can cover 80% of this area, but with a high confidence. So there's also this concept of confidence because the quality of the coverage. Then you formulate problems like that and you say, given these requirements, how can I satisfy them? Yes, so it's a trade. That's actually, you're making my point. You need both.
Yeah.
You need both to understand the best you can do if you have essentially an infinite number of resources. So you don't have to worry about cutting corners. Or if you have limited resources, you do it another way and you compare. Yeah,
Great.
I mean, this is what keeps us going. This is
Yes.
This is the essence of the research programs that we're running.
Yes, I think that's a big, because somehow I think it's kind of for a lot of research problem, while we can go into the depths of detailed algorithms, but a lot of times I feel the real challenge come really at the philosophical level, when we do some research, right? So it's
That's
kind
true.
of, the trade-off. So speak of that, so you talk about this, many people are doing this, optimization or algorithm development either at the protocol level or at the individual vehicle level to do research in support of this transportation automation in autonomous driven vehicles. So, and of course, earlier you mentioned, you now realize the importance of collaborating with, social scientists to better understand and better model human behavior. So one thing is that I'm just curious, when you started, before you kind of reach out to this human side, the social aspect of society, we are in our engineering world. Even in this kind of mathematical world, we are solving this kind of, we feel good, wow, we can solve all these optimization problems. And then because as you research more and more, you realize the need of getting to know better about human beings, and you reach out to other social science. But the thing is that when you get to that side of the road, did you get more optimistic, or did you get more pessimistic?
More optimistic for sure, because I can see the light of the knowledge and the opinions and the experience and skills of all these other colleagues who, until now, they were out there, but I didn't care or invest the time and energy to interact with. At the same time, it increases the level of complexity.
Yes.
Because now I have to learn their language and they have to learn my language. And to tell you the truth, talk about philosophical differences, I would say linguistic differences are also crucial.
Yes.
So speaking the same language as an economist or a policymaker or a public health expert is challenging. We talked as engineers in terms of, let's say, control and optimization, and we all have this picture in our minds when I say optimization or when I say constraint. I know exactly what I'm talking about, and I think most of us in this community know it. But when you talk to another person who has never really even formulated an optimization problem, then you have to still communicate, but at a different level. It requires a different language. And conversely, when they talk to me about their problems and their ways of thinking, sometimes I just completely, lose the ability to understand their insights, because they have certain insights. They have their own vision. I can't see it, and I need to see it to be able to productively communicate with these people. So optimistic, absolutely, because the opposite would be not communicating, maintaining our silos. We wouldn't have systems engineering programs. We would still proceed forward mechanical, electrical, civil, chemical engineering, which I don't think is the way to the future. I think it's pretty clear to me the way of the future is the interdisciplinary way. Here's a practical example. We teach the same courses sometimes in different departments. Say an introductory course on probability theory. In one department it's taught more like a statistics course, very elementary practical methods, because that's all they need. In other departments it's taught more like a very rigorous probability measure course. In other departments it might center more towards the Gaussian process, Markov process, because it's needed in the application domains of signal processing, communications, control. Why can't we teach a single course with the basic ideas of probability theory and random process and teach it across every department? Systems engineering would be the perfect home for such a course. And in fact, at Boston University, we do that. We have a course like that, which is taken by students from all the departments and from outside engineering, business school, computer science, biology. They take this course, and that way it's a better resource management if we have that one course instead of 3 or 4, as long as we do the job right, of course. Then it's much more efficient.
I very much agree with you. And actually, several years ago, when the Engineering College Council was here, for the College of Engineering, some council members suggested that system engineering should be taught to all the senior undergrad engineering, at least engineering students, because so that they can have that, and especially it kind of statistics and probability, because we're in this such an uncertain world. Whenever you want to categorize, uncertainty. Right. So after the reason I was asking whether you become optimistic or pessimistic, it's actually I totally agree with you, because the challenge we are facing is systems by nature, whether it's pandemic, climate change, food security, congestion. Those are all transdisciplinary challenges. A traditional civil engineer, a traditional electrical engineer, they won't be able to address that. But when I was asking you about it, when you reach out to consider the human factors, because you have been in the control world, optimization world, where you saying everything is under control, because there are just the objects. But then when you have the human factor coming in, I don't think you can control it anymore.
Yes.
So as a result, a lot of time it's compromising or trade off, and even, for example, imagine that if you have all the power based on your optimization and control, you say the world should be like this, and then when you see the humans, the world is like this. But I don't think you can say from optimization point of view, say the world. How can you move the world from here to here? You see it almost impossible. Right.
Yes. Yes. It is an ideal. But you can always strive towards that ideal and get as close as possible, which in our community we call a tracking problem. I can't perhaps, ideally track and reach perhaps a certain target point, like, I don't know, an object that I'm trying to track with a radar, but I can get as close as possible to that.
Yeah.
And in terms of the humans, I used to think of humans as noise. So there is noise, and I have to control my system, and I have these humans that may mess it up for me. But now we realize that humans are intelligent noise, if you will.
Uh-huh.
They are part of the system. They're a component of the system.
Human in the loop. Yeah.
Human in the loop. And so you have to make them part of the model.
But which we don't necessarily have as good in all those mathematics that we used for objects.
Exactly.
To model, the human. I know that is a kind of, it's kind of,
So that would be a source of pessimism.
Yeah.
You're right.
Yeah.
But I'm more optimistic because the more I talk to colleagues whose job and specialty is to model human behavior,
Mm-hmm.
I find that there is knowledge there. There's a lot of information that comes, and sometimes it's not necessarily quantitative, it is qualitative, but it's there. And we need to take that into account. Social scientists have the talent of a good social scientist, I think, is unlike us who develop good algorithms and proofs of theorems, is to design good experiments. So they formulate this hypothesis, and then they create an intelligent experiment with humans to see if their hypothesis is true or false, or anything in between. And in some cases, they formulate this hypothesis, and with the right experiment, it's almost like a proof. The experiment shows that the hypothesis is exactly, the people, the humans in the sample population behaved exactly as postulated. Now you have a proof, the best you can do. So there's a lot to learn. That's a different way of thinking than that of the more rigorous, regimented engineer or scientist. If I cannot have axioms and formulate theorems and use logical proofs, then I'm not doing anything.
Mm-hmm.
But there's more than that from social science that you can, and life sciences, by the way, also biology, I think, has the same characteristics because it relies a lot on smartly set up experiments as opposed to proving theorems.
Yeah.
So there's a lot we can learn.
Yeah, I agree. It sounds like going from the traditional physics to quantum physics. Remember, history, right? It's kind of
It's a different mindset.
Yeah, a different mindset.
Yeah.
So speaking of human factor, then I this morning when you were talking, you talk about this CAV control. Kind of imagine that what I call the platoon, like you call it
platoon.
It's platoon control, which is imagine that if we have homogeneous, just purely CAV, 100% CAVs, and you have these control things that work beautifully, right? That's nice. And then of course in the last part you talk about when the human driven vehicles come in, they could mess up the system. And of course in the conclusion slide you were saying that ongoing research you want to also look at what is the optimal percentage of the mix, right, of the CAVs and
Yes.
HDVs.
Yeah, and not necessarily optimal, but just find the sweet spot.
The sweet spot.
Where having more than 10, 20, whatever it is, X% of these smart cars pays off.
Mm-hmm.
So you might see a very, very small rise, and then suddenly a convex curve, which represents the benefit, the well-being, going up, taking off.
Yes.
Until, of course, you level off. Where is that sweet spot? We don't know yet. I showed you a case where if you do things right, the sweet spot is everywhere.
You
from
said
the
even
very
one,
beginning.
even one car.
Yes. Even one car can benefit,
Yeah.
or at least not hurt. And that's where we are. That's where the research stands. That remains to be seen, though.
So, so speaking of that, I think we're probably getting to the end. My second to last question is you think that this autonomous driven vehicle, autonomous transportation is coming, or so what's your view on this autonomous driven
I would say when I first started looking into that and giving talks of my then sort of very rudimentary research, I thought of that as science fiction, but you have to have science fiction before you get to the reality.
Yeah.
So science fiction to me meant, well, 50 years from now, yes, there will only be smart vehicles on the road. Then as I started getting more and more into it, in terms of seeing how some of these problems are perfectly solvable, realizing the statistic that I gave you before, 94% of all car accidents are caused by human error. Even if I can introduce a modest level of autonomy, I can cut that down. In the community, there are 5 levels of autonomy that people talk about, and of course the ideal is level 5, complete automation.
Yeah.
Where we are now is typically 2, like think of Tesla. So you can still do automation at the level of keeping your car within certain lanes and a little bit more.
Yeah.
We are moving towards 3 and 4. So I have become much more optimistic. It's not 50 years. In my mind, it could be 5 years, but it's not going to be 5 years because there are social obstacles, acceptance, practical obstacles, resources that have to be devoted. And I see it as something that within 10 years, perhaps, there will be, 10, 20, 30% of vehicles at some level of autonomy. So basically you will be driving and you'll be seeing cars around you with no drivers. That's the idea. And in San Francisco, you see that already.
Yeah.
So I'm much more optimistic in that respect. But who knows? I mean, that's what makes things exciting. There could be a major world event that changes that reality, for better or for worse. I don't know. But I'm optimistic and I'm excited because these are good problems. These are really good problems and for a good cause. The 94% accident statistic, I mean, if you can cut that down by half, that's important.
Yeah, I fully agree with you. And actually, I had a former PhD student, a system engineer PhD student. We worked on it, on the car following and lane changing behavior on the traffic flow. And we did see that, for example, and you mentioned this one big. For example, if you have one CAV, one smart car, to be the leading car, and that actually can bring a lot of benefit. Because usually people have the car following behavior, yes. Right? You don't even know. So that's why actually in the transportation community, we even said if we have a patrol police to every day to lead the traffic, yes. That can improve that.
Yes. I have a similar vision because in the example that I showed in my talk, the front cab is the policeman.
Yes.
He's setting the pace. In this case, it was a small platoon.
Yes.
But you could have many cars behind the human-driven vehicle and create a platoon that way. And the front one is like the policeman to set the pace. I have a similar vision of that.
That's great. So my final question, we're talking about this and we, I think, both agree upon and we're excited about, this system engineering or systems approach, trans-system approach. So, but apparently, and you mentioned, there are not many programs like this in the country all across the world. However, on the other hand, I feel we need many more people to have this kind of view, to be trained with this kind of tools. So what would you say to, the students either in your division or the system student here at Cornell or, over the world? Of course, you are familiar, like in COSI, right? They have all these. Yeah. So what would you say to like the future generation of system engineering, how they can, set up their goal and also like what kind of, like your understanding, what are the necessary, kind of knowledge pillars that you would urge them to do, to get trained such that, years later they can do things like you are doing and, taking a system approach.
Yeah, I mean, that's obviously a very broad and difficult question. It has to start, I think, with is there demand for systems engineers the way that you and I are describing them? Mm-hmm. And I think it's pretty clear. I mean, a lot of large companies are realizing that they cannot solve many of the problems with just super specialists. Mm-hmm. They need what we call the systems way of thinking. Yeah. If you solve one problem here, it may affect other components there, and you need to take that into account. So when you're designing the next generation plane, you know that if you tweak a certain part of the plane, the air conditioning, the ventilation system, you might cause an overload, let's say, somewhere else, which might affect the guidance system, which is even more critical. So you have to have that systems point of view. Mm-hmm. I think it helps to have also an optimization point of view because it's good to have a notion of performance and objective for how a system behaves. and to have a reasonably quantitative view of that. Are we talking about maximizing the throughput of a flow system in production or in transportation? Are we talking about monetary cost? Often in energy systems, that is, the pricing mechanisms are important, so you want to control and optimize that. So the demand has to be there, and I see it. I see it in companies that we talk to, where people say, yeah, that's what we like. We like people who think that way. Now, from the student point of view, I think it comes slowly as students, primarily undergraduates going through their 4 years traditionally of undergraduate education, they start realizing, some of them, not all of them, the ones that care about this way of thinking, that I need to know more. I can't over-specialize. I need to really maintain a broad spectrum. Those are the students that we get, and I'm sure you get here at Cornell. And so we get these students, and they're fertile minds for us to educate them and cultivate this interest. Beyond that, we need institutional support, right? I mean, we need our university to say, yes, we agree with that. Change is hard. So changing from having mechanical, electrical, civil, chemical to, we have, in our case at Boston University, we have the material science division, and we have the systems engineering division. Maybe we'll have another one soon. That's hard to accept, and it's difficult. Now, about your point about perhaps starting to educate undergraduates at the senior level on systems engineering, and maybe even creating a degree of systems engineering, that's something we've thought about a lot.
Okay.
But it's hard. And I don't want to get into the details, but I'm sure you're familiar with the problems. Already, we're trying to cram 4 years of an undergraduate education into the minds of students. And we all know that it should really be 5, maybe even 6 years if we really want them to learn everything and still maintain a well-rounded education, not just a very narrow, nerdy engineering education. We still want them to know their history and learn some languages and literature and so on. How do you fit all that in? It's impossible. At the same time, in the United States in particular, education is extremely expensive.
Yes.
So putting a 5th year where some of our seniors might say, now let's find more about systems engineering in the 5th year, that's impractical.
I see.
So in other countries though, I have seen more programs, even at the undergraduate level, which are closer to what we call systems engineering. They go under many different names, but I've seen in Europe, for example, I've seen programs like that, and they're quite popular. But I think in the US, we are limited by what I just said, and also preconceived notions where systems engineering, you find it as part of typically industrial engineering or operations research. I'm thinking of excellent programs like Georgia Tech, Wisconsin. These are industrial and systems engineering. And that is a different tack.
Yeah, more towards OR.
More towards OR and more towards, production systems, logistics. But we are talking about transportation. We're talking about public health. Those are systems as well.
That's right.
And you need a broader, way of thinking. But I don't know what are the right buttons to push to make these programs grow. At this point, I would say our challenge is to show that these programs are stable and successful. So you mentioned you have about 54 PhD students. We have about, I think, 45 or so, but the same order of magnitude. If we can sustain that and produce graduates who will represent our programs well and our philosophy well, both in academia and in industry, and hopefully also in public service, policy making. Actually, a systems engineer is probably ideally suited to have a quantitative background to go to Washington and advocate for a system solution to climate change crisis or energy crisis. You need a systems point of view to solve these problems.
Wonderful, Chris. Thank you so much. Your final sentence, I feel it really concludes our our discussion, I feel you talk about it's not only system engineer as approach, and also you want to have system engineer to really solve the real world problems. See, Ithaca in Boston, and hopefully even in Washington DC. Yeah, that's great.
Yeah.
Chris, I want to thank you again.
Thank you.
This is really nice conversation. Thank you.
Thank you. I enjoyed it very much.
Okay, I think we're all done.